Okay, so here we have topic 2.4, momentum impulse practice problems. I'm not going to do all of these. I will just do the ones circled and give you equations for 5 and 6. So I'm going to do 3, give you the equations for 5 and 6, 7, 8, 9 I'll do, 10, 11, 12, 13, 14, and 16. Let's begin. Show that the kinetic energy can be calculated directly from momentum using the following. E sub k, kinetic energy, equals p squared over 2m. So I'm going to show that this equation, I can derive this equation using 1/2, or E sub k equals 1/2 mv squared, and using linear momentum equals mass times velocity. So first thing, I'm going to look at this equation for kinetic energy that I have. E sub k equals 1/2 mv squared, and I'm just going to break that v squared into v times v. V times v is v squared. This m times v is momentum. So I'm going to replace m times v with momentum. E sub k equals 1/2 times p times v. Very close to my target, which is p squared over 2m. Maybe I can do something with this v. So if I look at v in my linear momentum equation, v equals p over m. Okay, so I'm going to replace p over m with this v here, and I get E sub k equals 1/2 p times p over m, which indeed is p squared over 2m. Okay, number 5, this is a pre-IB level question, but I'll still show you how to analyze it. A .140 kilogram baseball comes in at 40 meters per second, strikes the bat, and goes back out at 50 meters per second. If the collision lasts 1.20 milliseconds, find the impulse imparted to the ball from the bat during collision. So I'm going to draw a bat, okay, and then I have a ball coming in, and I will say that this initial velocity is negative 40 meters per second. The ball is going to leave with a velocity of 50 meters per second. Remember, velocity is speed plus direction. Okay, this is a bat. Okay, velocity is speed with direction. So if I have one direction going one way, the opposite direction is has an opposite sign. Sorry, I've hit the camera. Okay, and impulse, J, is m times delta v. So delta v is the final velocity minus the initial velocity. That's a positive 40, or positive 90. For number 6, we are now looking for the average force exerted. So I have to use the second equation for impulse. Impulse is the force of impact, or the thrust, times delta t. So I'll have the impulse from the first equation, from number 5, plug it in here, divide by 1.20 milliseconds. Remember, that's 1.20 e negative 3 seconds. And solve for my force. Number 7, this is an HL question. A ball of mass m collides with a vertical wall with an initial horizontal speed u and rebounds with a horizontal speed v. The graph shows the variation of the speed of the ball with time. What is the magnitude of the mean net force on the ball during the collision? Note that this is speed versus time and not velocity versus time. So I know that the net force for this will be the change in momentum over the change in time. In this case, I'm going to have to use mass times the average speed. So V average divided by delta t. The average speed is m times, I'm going to sum my two velocities. Obviously, this is when the collision happens between t1 and t2. I add up my velocities and divide by 2, and then the change in time is t2 minus t1, and I can further simplify this. I can bring the 1/2 down. So I have m times v plus u divided by 2 times t2 minus t1. And that's how you do it. Number 8, a stopper of mass 8 grams leaves the opening of a container that contains pressurized gas. Okay, so let's say this is part of some type of bottle or something that contains pressurized gas, and I have a stopper in here. So the pressure of the gas is going to exert a force on the stopper. The stopper accelerates from rest for a time of 16 milliseconds. So the time of this collision, delta t, is 16e negative 3 seconds. And the stopper leaves with a final velocity of 20 meters per second, or at a speed of 20 meters per second. What is the order of magnitude of the force acting on the stopper? Force is m delta v over delta t. Notice that delta v over delta t is acceleration, so F equals ma, and make sure to convert your mass, in this case, to kilograms, 8e negative 3 kilos, and 16e negative 3 seconds, and it's initially at rest. The final velocity is 20, so 20 divided by 16e negative 3 times 8e negative 3. Okay, number 9, a rocket engine consumes fuel and oxidizer at a rate of 275 kilograms per second. Normally we've been seeing change in momentum as m delta v, but we can also have change in mass, and we get the same result. So I'm looking for the thrust put out by the engine. So this is a change in momentum over a change in time. In this case, I have a changing mass, and I have an average speed. So I can do this delta m over delta t times average speed. In this case, my delta m over delta t is 275 kilograms per second. So I have 275 kilograms per second times my average speed of 1250 meters per second, and you can multiply those two and get the average thrust, or to get the thrust. Okay, going on. Number 10, two objects, M1 and M2, approach each other along a straight line with speeds v1 and v2 as shown. The objects collide and stick together. What is the total change in linear momentum of the system? Any type of collision, whether it's elastic or inelastic. This is an inelastic collision because the two objects stick together. For any type of collision, the change in momentum is always 0. This means that momentum is conserved. Momentum is conserved. And that's your answer. Okay, I'm going to give you help with these because for some reason people were having trouble. This is a pre-IB question, and you should be able to do this, but I'll still help. Two train cars having equal masses of 750 kilograms and velocities initial u1 equals 10 meters per second and u2 is 5 meters per second collide and hitch together. Determine the type of collision and calculate the final velocity. This is an inelastic collision. Check it. I have this 750 kilogram object. Initial velocity is 10 meters per second. It's going to collide with this train that's only going, this is a 750 kilogram train, and this one is only going 5 meters per second. In the end, so this is the before, after they're going to stick together. So after, they will have a combined mass, 750 times 2. This is 1,500 kilograms combined, and we want to look for their combined final velocity. So we use the conservation of momentum. Delta P is always 0, which means P final minus P initial is 0. So P final equals P initial. That is the sum of the momenta before equals their momenta after. So 750 times 10 plus 750 times 5 equals the 1,500 times V, and you'll solve for V. I know this is hard to see, I'm sorry. After, I'll write this up here. So 750 times 10 plus 750 times 5 equals 1,500 times our unknown V. Solve for V. Multiply these, add them together, divide by 1,500, you'll get your final velocity. Okay, so let's do this one. So a lot of people have trouble with this. Suppose a 0.020 kilogram bullet traveling horizontally at 300 meters per second strikes a 4 kilogram block of wood resting on a wood floor. The block bullet combo slides 6 meters before coming to a stop. Find the dynamic friction coefficient mu sub d between the block and the floor. Okay, so I'd be asked a lot of questions like this where you're asked to analyze the situation before and something after. So before, we're looking at a collision between the bullet and the block. So in this collision, I have a scenario where a bullet is fired and it travels with an initial velocity of 300 meters per second. This object is at rest. Then after collision, the bullet becomes embedded in the block and the two travel together at some new final velocity. This is an inelastic collision. So I have change in momentum is conserved. So I have the mass of the bullet, 0.02, times the velocity of the bullet to give me its momentum. This momentum gets transferred to the combined system. So this is equal to their combined mass, 4.0 plus 0.02, 4.02 times their final velocity. I'll get their final velocity. Go ahead and calculate that for you. 300 times 0.02 divided by 4.02 gives me a velocity of this system, 1.49 meters per second. Now, this is where friction starts acting. So now that the block and the bullet are in motion together, the force of friction acts to oppose this velocity. So the final velocity from our collision becomes the initial velocity of our work kinetic energy situation, where now the force of friction does work to the block bullet combo to bring it to a final velocity of 0 meters per second. So we have to get the dynamic friction coefficient, I have to use the work energy theorem, which states that work equals the change in kinetic energy. Work is done by the force of friction. So work is force of friction times the displacement times cosine of the angle between the displacement and the force applied, and I set that equal to the change in kinetic energy. E sub k final is 0 because the final velocity is 0, minus 1/2 their combined mass, 4.02, times the initial velocity, 1.49 squared. Okay, force of friction is mu times force normal. The force normal is the 4.02, their combined mass, times g. It's displaced 6 meters. Cosine of the angle is -1 because cosine of theta, the displacement is this, force of friction is the opposite direction, so cosine of the theta is 180 degrees. Cosine of 180 degrees equals -1. This becomes negative equals -1/2 0.5 times 4.02 times 1.49 squared. So this is a negative 4.48 joules. So I will now, the negatives will cancel, and you can solve for mu. Mu equals 4.48 divided by 6 times g times 4.02. All in parentheses, you should get a number less than 1. And it's unitless. Okay, number 13, two identical spheres, each of mass m and speed v, travel towards each other on a frictionless surface in a vacuum. Which of the following statements is correct regarding the spheres post-collision? So first thing, I don't know if this is an inelastic collision or an elastic collision. It doesn't tell me. So I need to look at the answer choices and figure out what is the best. So we are trying to figure out which of these is correct for the spheres after collision. So letter A, the total momentum of the spheres is 2mv. Well, let's see. Change in momentum for any type of collision is 0, which means that the initial momentum should equal the final momentum. What we're looking at is a picture of the initial, which will tell us what the conditions are after the collision, post-collision. So initially this has a momentum of positive m times v. Initially this has a momentum of negative m times v because velocity is a vector. Negative m times v. Speed with direction. So initially I have mv plus a negative mv, which means that the initial momentum is 0. The initial momentum of this system is 0, or the total momentum before, which means that the total momentum has to be 0 after, so A is not correct. B, after post-collision, each sphere has 0 momentum. Maybe, potentially, I don't know yet. I don't know what type of collision this is, so I'm going to come back to this one. I can't eliminate that possibility with what my givens are. C, the total kinetic energy of the spheres is mv squared. Maybe. This is definitely true if it's an elastic collision. So if these two spheres bounce off of each other, for an elastic collision, kinetic energy is conserved. The change in E sub k is 0. So here I see I have a kinetic energy for this before collision of 1/2 mv squared plus 1/2 mv squared. This is the kinetic energy of this plus the kinetic energy of this one gives me mv squared total. So that's before. I don't yet know for after. Each sphere has 0 kinetic energy afterwards. That can't be true. If each sphere has 0 momentum, that means each sphere has no velocity because the mass doesn't change. If each sphere has 0 kinetic energy, this means that each sphere also has 0 velocity because kinetic energy is the energy of motion. This means that B and D are telling me the exact same thing, so they both can't be correct. The only choice is C. This means that, okay, even though they didn't tell me it was an elastic collision, it is an elastic collision because the total kinetic energy of the spheres afterwards is the same as the kinetic energy of the spheres beforehand, mv squared. So C is the only possible choice. Okay, number 14, a stationary nucleus of polonium-210. So I'm just going to draw my situation here. I have polonium-210, undergoes alpha decay. So this is kind of like an explosion, which is an inelastic collision in reverse. But momentum for any type of collision is conserved. Delta P is 0. The initial speed of the alpha particle is v. What is the speed of the lead-206 nucleus in terms of v? So initially the polonium-210 has no momentum, which means that the final momentum of the lead-206 and the alpha particle should be 0. Just for reference, an alpha particle is a helium atom, and this has an atomic mass of 4 atomic mass units, 4 AMU. We don't need to convert the masses in this case. So that means that the momentum for the alpha particle plus the momentum for lead-206 equals 0. So I have my helium, I have my lead-206, both the momentum will be conserved between them. So let me finish this equation. My alpha particle has a mass of 4 and a velocity of v. The lead-206 has an atomic mass, 206, times my unknown velocity, which I'm calling x, that's equal to 0. I'll subtract 206x from both sides. 4v equals negative 206 times x, and then I'll solve for x. The velocity for x is negative 4 times v over 206, but remember we're looking for the speed, so I just make this positive, and this is my final answer. X, which is the unknown speed in terms of v, 4 times v over 206. I'm going to let you answer this question, number 15. And finally, I have number 16, last one, yay. The graph shows the variation with time t of the force F acting on an object of mass 1.5 e 4 kilograms. The object is at rest at t equals 0. What is the speed of the object when t equals 30? It's not 0. Everyone kept saying 0. Notice this is the kilonewton. The force, this is thousands of newtons. So this is an F delta t equals m delta v. This is an impulse. Anytime you see a force versus time, you need to think impulse. You need to think a change in momentum. So I have, if I take the area under this curve, I get an impulse. So the area is the force, this is 1/2 times base, which is 30, times a height of 6e3 newtons equals a mass, which is 1.5 e4 kilograms, times a change in velocity. The object is initially at rest, t equals 0. So the change in velocity, so I only have v final minus v initial, so this will give me my v final. I can then solve for v final, and this will tell me what the speed is at 30 seconds. So solve this expression, solve it for v final. I thank you for watching this video. I hope you find this helpful, and study well.